Hello everyone, this is Dr. Young, and in this video we are going to briefly talk about an anti-Markovnikov addition of HBr that involves actually a radical pathway, not the pathway that you've seen with normal additions to alkenes. So I have there, it's radical halogenation. Actually, I should probably modify that. It's not a fully a halogenation, it's a radical hydrohalogenation. So sorry, hydrohalogenation, because you're adding a hydrogen also. You'll recall from previous reactions with alkenes, right, that if you take HBr, so hydrobromic acid, and we said this worked with any halogen-based acids, so hydrochloric acid, hydroiodic acid. And in our mechanism, we had the alkene go and get the H+. That gave you the more stable carbocation, so in this case tertiary versus secondary. And then we said that the bromine would add to that tertiary carbocation to give us our product, right? And this was a Markovnikov addition because the nucleophile went to the more substituted carbon, the H went to the less. So Markovnikov addition. Markovnikov addition. And right, the bromine went to the more substituted, right? Because if I look at this, this is a secondary carbon versus a tertiary carbon. But in this example below, I didn't have it go to the tertiary carbon. I had the bromine go to the secondary carbon. This is an anti-Markovnikov addition of HBr. So it goes to the other carbon. And I need to note here too, this is important, is only works with HBr. While with this up here, right, like I said before, it could be HCl, it could be HBr, HI, etc. This only works with HBr. You can't add HCl and peroxides and get something different, or HI and peroxides. And it just has to do with the energy levels and stabilities of the different radical intermediates. We're not going to go into all of that right now, but I want you to know that it only works with HBr. But it can be a useful tool, which we'll see in a sec. And this goes through a totally different mechanism. Because there's peroxides involved, the idea is that this peroxides allows us to go through a radical mechanism. Whereas up here, right, we didn't have a radical mechanism. This is just our normal two-headed arrows. We had all of the heterolytic cleavages. This is going to involve all homolytic cleavages and radicals. So let's take a look at what the mechanism is going to look like. So here I have a really simple example of just a propene turning into a 1-bromopropane. And I'm going to go ahead and draw out, right, this is going to have sort of initiation, propagation, termination steps because it's a radical reaction. So I'm going to start with the initiation steps. I'm not spelling so well right now. Initiation steps. What we're going to have first is whatever our peroxide is. I left it just generically R, but it could be like some T-butyl peroxides or benzoyl peroxide or even hydrogen peroxide. But the idea is that the peroxide is very unstable. And so what we're going to see is we're going to see that peroxide bond break. Right? And remember that peroxides are unstable because you've got two oxygens, which are very electronegative. They want those electrons. Plus, those oxygens each have 4 unpaired electrons in these 2 different orbitals on it, right? So you've got all of these electrons on the oxygens repelling each other, creates a little strain there, makes it high energy, plus the oxygens want to take back electrons. So that bond is very weak. It's very easy to break. So in this initiation step here, that bond's going to break, which is going to give me 2 of these alkoxy radicals, where I'm going to have an RO with just 1 electron. And what's going to happen is that that alkoxy radical, in the second part of this step, is going to react with my HBr. And what we see is that the alkoxy radical is going to abstract a hydrogen. So of the 2 hydrogens, or sorry, the 2 electrons that were in the HBr bond, the radical from the oxygen is going to combine with the one of the electrons that belongs to the H, and then the other radical, the other electron, is going to land on the bromine. So we're going to have an alcohol at the end, ROH, and we're going to have a bromine radical. Now it's this bromine radical that goes into the propagation steps. So now we're into the propagation steps, right? We've made the bromine radical. And then what we're going to see here is we're going to have a pair of steps that just keeps on recreating this bromine radical. So I turned my alkene around just to kind of show us here. The idea here is that the pi electrons, right, those are relatively high energy electrons. They're easy to do stuff with. They're easy to get to. And so when you expose them to a radical, they're going to react with that radical. And so I can have this radical combined with the electrons in this alkene. I'll draw them here in blue. Like this. And what we're going to see is that the bromine is going to add in a way such that I leave behind a secondary radical. Right, that's a secondary radical. You can imagine, I'll put this in red, this will be parenthetic, this is not going to happen, but you could imagine the bromine radical, right, instead reacting with an electron from the other side and leaving behind a primary radical. But again, that's not going to be nearly as stable, right? That's a primary radical versus a secondary radical. We know that secondary radicals are more stable, which is why the bromine adds to the less substituted carbon, not the more. So I'll put not seen, and I'll say up here, forms the more stable radical. So I've made that, I have that bromine attached, and I have an alkyl radical now. That alkyl radical is still part of the propagation steps, where it finds some unreacted HBr, right, because you have a whole bunch of HBr and you just initiated this reaction, added a little bit of peroxides. And then that alkyl radical is going to, that alkyl radical is going to abstract a hydrogen. Come on, friend. Go away. I will erase you. There we go. Let's try that again. Radical here. This radical will combine with one of the electrons from the HBr. The other electron is going to sit back on the bromine, which gives us our product. Right, I'll draw this H here, but right, we don't draw CHs normally. And then you create another bromine radical. And just like with the radical halogenation, right, the idea is that this bromine radical that you formed here is the same bromine radical in this first propagation step that then reacts with the alkene, makes this. This alkyl radical reacts with HBr to make more bromine radical. And so you just go round and round and round with these two, right? These two steps are the propagation steps. Again, just ignore what I wrote in red. That is not the way the mechanism goes. And I'm going to save myself and yourself a little bit of time here. You can imagine that there would be termination steps. Termination steps here also. I'm not going to draw any, but again, you just combine two radicals. Right, to get the termination steps. But that's what allows us to see, right, the fact that the bromine added not on the secondary carbon, but on the primary carbon. So when we look at our product here, primary carbon, secondary carbon, we added the bromine to the less substituted carbon in that alkene. Let's just quickly look at a couple of examples. Should be pretty straightforward for these top ones. And here's a synthesis problem. I'm going to pause here. I'm going to stop talking. I recommend that you pause this video. Take a chance to just slap on your bromine on these and see if you can figure out that synthesis problem. Okay, so if we look at this, right, all you need to be able to do is figure out which is the less substituted carbon, put the bromine on there. So here I have secondary versus tertiary. So I'm just going to put the bromine on the secondary. No more alkene because you've added an H and a Br on there, right? This is an addition reaction overall. And that would be my major product, right? The less substituted carbon got the bromine. Same thing for this one. Bromine should be on the secondary, not the tertiary. Here we have a primary versus a tertiary. Definitely a big difference there. So those would be my three products for these, right? A hydrogen added, a bromine added. I didn't draw the hydrogen because we don't draw CHs, but that's where your bromine goes. Now in a synthesis problem like this, you can kind of save yourself some time. There are other ways to get a good leaving group on a less substituted carbon, but now this is going to save us a little bit of time. So I see that I have an alkyl halide, and I see that I have, looks like an OCH3 added here to this carbon out here. So I need to figure out a way to get OCH3 out there. One way, and again, there's many ways you can approach these, but one way is I could just add a big bulky base, so something like LDA or T-butoxide, because I know that will do an E2 reaction that gets me an alkene like that. And once I have an alkene like that, I know how I can get some functionality on that carbon out there. Before we said you could use hydroboration to get an OH out there. That would work. But then you'd have to turn that OH into a better leaving group like bromine. So you'd do hydroboration then like PBr3 or something. But now I know that I can just go ahead and skip that and I can just get a bromine out there right away. So I'll just add HBr and some peroxides, whichever one you want. Now that I have a bromine out there, I can just do an SN2 with like sodium methoxide. And again, SN2 should be the major product because that's just a primary alkyl halide, not like a secondary or tertiary. So this would be a way that you could do that synthesis. So I hope that clarifies some questions about this anti-Markovnikov addition of HBr. Remember, it's just bromine, goes through radical mechanism. It would have a mixture of enantiomers if you formed a stereocenter. I didn't write that out for any of these. But technically, that's a stereocenter, that's a stereocenter. So you'd have two different products at least, right, where you have a dash and a wedge. But that's basically it. Hopefully, short video, pretty straightforward, can be very useful synthetically. So study up, do some practice, good luck.